Here we are at the beginning of that journey, and all the pieces are now finally coming together.
It seems to. And talking about what you achieved, I brought an example. You know that HD Hyundai. I mean, they built ships, huge ships, and shipyards, by the way, and they use our technology.
That's right.
They're sitting on NVIDIA.
This is a digital twin of an entire ship. Every nut and bolt is in there. It's incredible.
I mean,
this is the full CAD of the ship.
Visited
the perfect, precise digital twin.
And you see also the people working on the ships. You simulate everything. By the way, these ships they look alike. So the body is the same, but each one of them is individual. So you really have to be very, very clear how you design it, you optimize in the digital world, and then you build it, not that's before right. that. And that's where our whole stack comes together, complementary technology. For the photorealistic representation, we use Omniverse.
This is really quite a perfect example of the type of work that we do together in this realization of this digital twin idea. That you would design every aspect of engineering. It's not just the CAD, but the computing, the electronics, all of it would be integrated and built into a digital twin. It would, of course, run all of the software in the digital twin. And in the future, I hope this digital twin of a ship will actually put it in the ocean, a virtual simulation of the ocean, and see it completely operate.
Exactly.
Yeah.
And you have only one option to get it onto water. If that fails, you have a problem, by the way. So, well, we talked about bringing our partnership to the next level. And the whole idea is obviously to take these examples and scale them even faster. And of course, to make it AI enabled. I'm talking about industrial AI, which really hits the real world. And we picked 5 areas of collaboration where we want to intensify, and that is good news for our customers too, I guess. Let me start with the first one, take them now one by one. The first one is AI native chip design. So if it comes to chip design, I don't need to tell you something. Obviously, with each next generation, you're getting closer to the physical limits. So tell me what the challenges are and what can we do?
Well, let's use our latest generation that we just announced yesterday as an example.
Congratulations.
So Vera Rubin, in order to build the latest generation GPU, people think that our GPU is a chip. It is a chip. It consists of a chip. But ultimately, in order for these GPUs to scale up to process the level of AI that's necessary at the frontier, these GPUs are essentially one giant rack. And this entire rack is, in the case of Vera Rubin, 240 kilowatts. It consists of altogether 220 trillion transistors. We had to design 6 different unique chips: CPU, GPU, networking, multiple types of networking switches. One is for scale up, one is for scale out, and a smart NIC and a data processor for storage, all for AI memory, basically. All of this stuff came together. Is 220 trillion transistors is 2 tons, and 150,000 engineering years came together to build this one system that we announced yesterday. And in order to do this perfectly at a rhythm that our company runs at, the level of chip design, system integration, thermals, electricals, all of that, in a lot of ways, our GPUs is a little bit like that HD Hyundai ship.
Yes.
And what we are hoping for, and the reason why we're partnering so closely together, is so that we could build that Vera Rubin in the future as a digital twin. The entire system as a digital twin, not just the chips, but the systems, the chips, everything together, cooling, thermals, and run the thermal simulation directly through it as it is a digital twin. And that's our vision. And so we're accelerating. The first part of our project together, our partnership, is to accelerate Siemens EDA, Siemens Sim Center, accelerate everything we can with GPUs. And this way, we could scale up the simulations that we do and achieve the virtual digital twin that we hope for.
So what we're going to do is we will use Yakuda software. We will rewrite our EDA software so it can take advantage of GPUs.
That's right.
So working with GPUs and designing GPUs.
Imagine EDA software being 100 times faster.
Exactly.
Or being able to scale up 1,000,000 times more, right? That's our hope and dreams.
But we don't stop there. Still, we talk about AI native chip design. What we want to do now, we want to train our technology, our models on a massive amount of data so that it's not only about validation of design, but really making a proposal of new designs in EDA. This is breakthrough. It's never done before. That's what we're heading for.
The goal of an engineer is not to write Verilog. That's not the goal of the engineer. The goal of an engineer, of course, is to solve problems, imagine great solutions. And it would be incredible one day. There would be agentic Siemens EDA designers that are sitting with our designers.
Exactly.
And they're exploring ideas together, trying iterations and exploring boundaries.
Number two, we talk about same thing here, AI native simulation. So when it comes to simulation, obviously this is a lot of number crunching, and it very often still runs on CPUs. This in the first step, we want to bring this technology, the heavy number crunching elements of our simulation to GPUs. That again accelerates X times, 100 times, 1,000 times. And if you can, I mean, there's an example. This is a car simulation, by the way. It goes back to when we started off our partnership is from BMW, where we simulate the airflow, the aerodynamics, and it's a lot of consumption and it takes a lot of time. So if you speed it up 1,000 times, you can do much, much more iterations. Again, we do not stop there. We want to have simulation not only to validate, but to create.
That's right.
Again, you need a lot of data. You need our technologies, and that's where NVIDIA has.
This is our technology running in real time. Our technology together, isn't it? You know, simulations, physics is beautiful. I mean, that's just the bottom line. Numbers are beautiful.
We do that.
Only an engineer would say that. Numbers are just so beautiful.
And we do that for trains. And again, we're using physics Nemo from NVIDIA and the full Siemens simulation stack with our
Siemens has the world's leading suite for industrial simulations, and SimCenter and all of the suites of solvers in SimCenter. We're going to accelerate completely using CUDA and CUDA-X. We are also going to work together to create AI physics, to teach AI the laws of physics so that it could emulate physics, not to simulate physics from first principles, but emulate the outcome of physics, essentially guessing where the physical properties are going to go at the next second or the next nanosecond, the next microsecond, the next second. And by doing so, we could speed up physics simulations, physics experimentations, if you will, 10,000 times, 100,000 times, and essentially create a real-life digital twin of a wind tunnel. We essentially put a real design into it, right? Real digital twin design into a digital twin of a wind tunnel and see it work. And so the opportunity to do all of these experimentation in real time is really exciting.
Which brings me, talking about physics, the real world, physical AI, which brings me to the third area where we step up, which is AI-driven adaptive manufacturing. So, this always reminds me when we talk about our technology stack, what we want to bring to the plants, which reminds me what you always say. I mean, actually, a plant is almost like a robot, isn't it? It's a big robot. So
exactly.
Or a car.
If you look at a car today, it's sensors connected to a computer. That computer is running software defined, and today the software that we run on top of it is largely AI. Well, that car is going to be made inside a factory that has sensors running computers, Siemens software stack and operating systems, and all the AIs that you'll have running on top of that. In a lot of ways, that factory, the car is an inside-out AI. The factory is an outside-in AI. And it's going to look at the cars that it's going to build, and it's going to build it robotically. So the entire factory is going to be one giant robot. It's going to orchestrate a whole bunch of robots that themselves are robotic, and they're going to make products like cars that are software defined and robots. So it's going to be robots orchestrating robots, building robots, in the future. And so this level of integration of technology has never been achieved before.
Exactly.
And so it's really the reason why we have to build the foundation of future manufacturing from the ground up. And nobody could do it better than Siemens because you're already the operating system of manufacturing plants all over the world. And so from that baseline, we're going to, number one, make it software defined, and then two, make it AI driven. And all of that, it's so great to see you drive that vision and for Siemens to really make that possible for the world.
And we're
going to use it ourselves.
Exactly. We're going to start in Germany in 2026, a first fully AI-driven adaptive manufacturing site. We bring an AI brain on top of our software-defined automation and our operation software, which basically consumes what a digital twin produces. And here comes the beauty, we do that in real time.
That's right.
In real time, so you can really control the manufacturing side.
So our partnership, we work together and run Siemens factories. Meanwhile, we have our partner, Foxconn, working with us in the United States to run the factories for building AI supercomputers. And so this partnership is really incredible. We've talked about design, we talked about simulation, now we're talking about manufacturing, all powered by GPUs, all powered by CUDA, all powered by Siemens, and all powered by AI.
And you see in the back an example of how Foxconn is using the technology already. And again, the AI layer on top, the AI brain, with connects to the real world data and real time data makes the.
And it looks so real, but this is a digital twin.
It's a digital twin.
This looks so incredibly real, and that's really the whole purpose of the digital twin. It has to, in every physically important way and operationally important way, it has to be a perfect representation. And so the ideal is that the digital twin and the real version of it, there is no ability for the computer to know the difference. It's to the extent that our AIs can't tell the difference between whether they're inside a digital twin or inside the physical world. That's our goal.
Exactly.
Yeah.
There are other factories too. They produce intelligence. We call it AI factories. So that's the next area of collaboration. And I know that when you talk about Vera Rubin, you need obviously new AI factories. They have to be signed differently. And you're building one on your own as we speak.
Yeah.
So we might want to share about the challenges, what needs to be different.
Well, if you take a look at the reason why I don't call it a data center is a place where people store data. These plants, in the case of a 1 gigawatt data center or 1 gigawatt AI factory, it's $50 billion. The investment level is unheard of of any type of factory ever the world's ever built. The amount of technology inside is incredible. And so if you're building something that costs $50 billion, you want to make sure there's absolutely zero scheduled delay. You're not going to be able to tolerate design changes. You're going to have to make sure that we create the digital twin, we plan it up front, we simulate everything up front. We're pushing the power, we're putting electricity, we're going to push cooling all the way to the limit. And so if we don't simulate this entire this factory in a digital twin, we have no chance of success. Yes. And then of course, once you operate it, managing all of these computers, these AI supercomputers, the networking, the storage, and running it all at the precision we need to run it at, the control of it is incredible. So you're controlling, of course, the management of the systems, you're controlling the power, you're controlling the cooling, and this entire system is essentially one giant factory and is running all the time. And so when you put that much capital at work, you better make sure that the uptime is perfect and always, and that you're going to make sure that your scheduled delay is basically zero. And without us working together and building these together in a digital twin, the chance of success is extremely low.
Exactly.
Yeah.
We can build them faster.
This is no different. Roland, this is no different than NVIDIA today. The idea that we would design chips without software is completely illogical. Exactly. Right? The idea that you would design these electronic systems without design software and verification software and simulation, come on, forget it. And so in the future, the idea that we would build plants, manufacturing plants, whether it's a car plant or a chip plant or an AI factory plant, the idea that we would build any of them without first doing it in a digital twin is completely inconceivable. And the idea that we would be able to operate these incredibly complex systems without artificial intelligence, completely inconceivable. And so I think that we know that future is here, and we know that the stakes are incredibly high. And that's the reason why our partnership with Siemens is so important to me.
We build this blueprint designs for our factories together. We have automation technology, which is much faster. It's industrial automation technology because the demand pattern of AI factories is so fluctuating. We know how to connect them to grids because we know how to operate grids. But we have
You've been doing it for 175 years.
Exactly. We do that. We know how to do that.
After 175 years, you're going to get good at something.
Well, and what we also do for more than 175 years is using our own technology.
That's right, yeah.
Which is the last area we want. I mean, actually, the people said, don't use the saying, we drink our own champagne. So now we modified it, we drink our own beer or whatever.
That's right, German company.
But we actually, we use each other technologies.
That's
we look
right.
deeper into it. What can we do more and better? And it starts, for example, with the plant in Germany I was talking about. We talk about EDA, software simulation, and bringing that to the next level to speed up our each other's development.
It's incredible. We're gonna work together to accelerate all of your EDA software, which we can then use to design our chips faster, so that we could accelerate your EDA software faster. We're gonna accelerate all of your SimCenter software, so that we could use it to design and simulate our AI factories faster, so that we could create AIs that makes SimCenter faster. And if you look at this, and we're gonna use Siemens so that we could automate our factories to build even more amazing supercomputers, so that we could create AIs to make your AI factories even more productive.
Doesn't that sound like the perfect partnership of two companies coming together?
Yeah. And that's why whenever Roland reaches out and he needs a bug fix, I fix it right away. because I fix his bug, which directly comes back to my company, and my engineers go faster.
And I tell you, this works in both ways. So they're scared when you have a call. So Jensen, thank you very much for the partnership.
Thank you.
Best is ahead of us, and looking forward
this is
to what we do.
We are at the beginning of a new industrial revolution, and what perfect company for all of that capability to come together than the company at the center of every industrial revolution. And so it's a great privilege to partner with Siemens, and it's incredible to be friends with you, and to see your vision of Siemens come together, and for our journey of reinventing industry to achieve this milestone is incredible. So thank you.
Siemens and NVIDIA building the industrial operation system. Jensen, thank you.